Hey folks, welcome back. So this is another data analysis video. Continuing on from the previous video about multiple regression, what I'm going to do is in this video fit a multiple regression model that also includes some categorical predictors, so categorical independent variables. So remember, multiple regression analysis, it allows us to investigate the relationship between multiple independent variables, IVs, and a scale dependent variable, or DV. In a previous video, in the last video, I demonstrated how to run a multiple regression analysis and interpret the results of the model. That example included multiple independent variables that were all measured on some sort of scale, either discrete or continuous. However, when conducting multiple regression, we can also include categorical predictors or independent variables in the model along with scale independent variables. So when including categorical variables in a multiple regression analysis, one of the categories is taken as a reference value, and differences in scores on the DV between categories are indicated as differences between the reference category and the comparison category. So to achieve this, we have to create new variables containing dummy codes that indicate which is the reference category and which is or are the comparison categories. So that means creating n-1 dummy variables, where n is the number of categories in our categorical independent variable we're including in the model. So when running these analyses using the stats model software library, sometimes stats models will recognize that a variable is categorical and automatically create those dummy codes for you. However, if the variable isn't recognized as a categorical object, or if you want greater control over the analysis, it's often better to dummy code the variables manually before running the analysis. And you can do that quite easily, using the pandas get dummies method. So what I'll do in this particular notebook and video is I'll demonstrate how to run multiple regression using stats models and including categorical variables. I'll do this using a data set relating to insurance premiums in the US. It's quite a well-known and openly available data set. It's commonly used in kind of machine learning and things like that for education and training, I guess. And the multiple regression model that'll fit, it'll assess whether we can predict a participant's insurance expenses using scale independent variables of age and body mass index, or BMI, as well as categorical independent variables of the region of the US that the participant lives in, and that contains 4 categories: northeast, southeast, southwest, northwest, and whether or not they're a smoker, which contains 2 categories, yes or no. So 2 categorical variables, 2 scale independent variables in the model to predict insurance premiums, I think, and insurance costs, essentially. All right, so I'm going to import a number of different libraries that are going to be useful for the analysis. I'm going to import pandas, numpy, matplotlib, stats models, and scipy. And I'm going to import this data set. I've got it saved on my laptop as insurance.csv. I'm going to import it using the pandas pd.read_csv method. I'm going to save it as an object called df, short for data frame. So let's have a look at that. And you can see here, if we look at the header, we've got different variables here in the columns: age, sex, female, male, BMI, which is obviously some sort of decimal, children, it's kind of a count of number of children, smoker, yes or no, regions, southwest, southeast, northwest, etc., and expenses, which is probably some sort of dollar amount representing insurance premium, maybe something like that. If we look at the info for the data set, it's a really big data set. 1,338 participants, and we can see that each variable has 1,338 non-null data entries, indicating or suggesting that there's no missing data in this case. We can also see the data types for our variable. So the DV, which is going to be expenses, is a floating point variable, so that's going to be essential, as when we're using multiple regression, we're predicting scores on a scale DV. And the IVs of interest all seem to have appropriate data types for the analysis we want to conduct. The 2 scale independent variables, age and BMI, are shown as being of integer and floating point. So age, integer, BMI, floating point. Data types, respectively, which is suitable. And the two categorical IVs we also want to include in this analysis, smoker and region, are shown as having the object data type, so smoker and region. So they're saved as kind of string objects essentially, which is absolutely fine. And so it suggests we don't really need to do any data wrangling to tidy up the data prior to running this analysis. So what I'll do first of all is I will fit this multiple regression model using stats models. I'm not going to put the whole thing in to start with. What I'll do in the first model here that I'm going to run is I'll include the two scale independent variables, age and BMI, and only one of the categorical independent variables, region, there. So you can see I'm using these kind of R-style formulas as stats models allows you to. I'm creating this object called model 1 using SMF, stats model formulas.ols, ordinary least squares. The formula that I'm passing is passed as a string. Expenses, RDV, is a function of age plus BMI plus region. I'm using a nice one-liner, .fit, and if we run this, we'll get some nice regression output, a kind of a model fit table, a coefficients table, and various other things. So what we can see in the above output is that we have a significant multiple regression model if we inspect the F statistic associated with the model. So we can see I'll point it out in a second on the table. We've got F and degrees of freedom 5 and 1332. Our F value is 36.47 if we round that, and P is less than 0.001. So let's have a look at that. So if we look at our F statistics, our degrees of freedom are 5 and 1332. F is 36.47. The P associated with the F statistic is kind of very, very small indeed. It's 4.30 times e to the negative 35. It's a very, very small value. We'd have to move that decimal like 35 places to the left. So I've just specified it precisely, reasonably precisely, as less than 0.001. Okay, so we've got a statistical regression model that's telling us that fitting this multiple regression model is better than just using the mean value of our DV expenses to predict what someone's insurance expense is going to be, essentially. Okay, so if we look at the coefficients table, it gives us the beta coefficients or the slope for the regression line associated with each of the independent variables. And it tells us if that variable is a significant predictor in the model. So we can see the scale IVs are both significant. So we've got age as a coefficient beta value slope equal to 242.94, and the associated t statistic for that is t, degrees of freedom of 1332. Yeah, the t value is 10.89, p is less than 0.001, and for the BMI, it's got a beta value slope of 321.82, and the associated t statistic is degrees of freedom are 1332, t statistic is 6.0, p is less than 0.001. So you can see that there in the coefficients table, age and BMI. There's our coefficient for age, there it is for BMI, 242.94, 321.82, and our t value for each one. And the p, it's shown as 0.000, so it's less than 0.001. Not sure how small it is exactly because this is only rounded. It's only displayed to 3 decimal places, but it could be very small indeed. Okay, so those two scale independent variables seem to be significant predictors of insurance expenses, age and BMI. Okay, and importantly, so we can also see that the region categorical independent variable has been automatically dummy coded, and the beta coefficients are given for 3 of the 4 regions. These are northwest, southeast, and southwest. So let's have a look at that. So there you are. You can see in the coefficients table we've got region northwest and region southeast, region southwest. They've got associated coefficients and they've got associated t values and p values with them, telling us whether they're significant contributors to the model or not. So the fourth category that's missing is northeast. and that is the one that's been used as the reference category for the analysis. So the coefficients shown indicate that, say, the change in DV scores for that region relative to the northeast reference category region. So, for example, if we look at the northwest, this has got a coefficient of negative 979.66. You can see that there. If we round it to 2 decimal places, yeah, what this indicates is that change in region from northeast to northwest results in a reduction in units on the expenses DV. So effectively, insurance expenses are lower in the northwest region is kind of what we could interpret that to mean. But note though that the associated t-values for all three region categories are not significant. So if we look at all three of those, these are the t-values, and all the p-values associated with them are non-significant. Okay, so that indicates that the different levels of the region independent variable, they're not contributing significantly to the multiple regression model. So this appears to show that the region someone lives in is not a predictor of how much they will pay in terms of insurance premium expenses. I assume this is health insurance in some way or something like that. Okay, so what I'll do now is I'll rerun the analysis and include the second categorical variable, which independent variable, which is smoker. So above we used age, BMI, and region. Now we'll use age, BMI, region, and whether someone is a smoker or not, to see if this predicts insurance premium expenses. And on this occasion, what I'll do is I'll manually create the dummy coded variables for the two categorical independent variables. Although we didn't need to do that here, stats models did that for us. There was no work for us to do here for the region independent variable. Stats models recognized it was a categorical variable and it dummy coded it for us. It's useful to know how to do this in case the software library that you're using to run the model doesn't automatically recognize that the variable is categorical. One other thing before we move on, because it's kind of going to be relevant when we add this next predictor, is for this model overall, we've got a significant model. Age and BMI seem to be the significant predictors, region doesn't. And we've got an R-squared value of 0.12, so about 12% of the variance in premium expenses seems to be accounted for by age and BMI, essentially, with region not really contributing anything. All right, so what I'm going to do here is I'm going to use the pandas get dummies method to dummy code the two categorical variables. So I'm going to take our data frame df using pd.get_dummies, and what I'm passing to it is the data frame we want to use, which also has I'm not changing it. I'm not saving it as data frame 2 or anything like that. I'm just kind of passing I'm basically changing the existing original data frame. So I'm passing the data frame as an argument, columns equals, and then I've passed it a list, smoker and region. Yeah, so what I'm doing is I'm saying take the data frame and take the column smoker and regions and get dummies for them. Drop first equals true. So above, what we can see here in this cell is if I run this, boom, there you go, we can see that 4 new variables, smoker yes, region northwest, region southeast, region north southwest, 4 new variables have been appended to the data frame. So these are the dummy coded levels of the categorical variables. So we've done both of them, smoker and region. So the dummy code for smoker has taken now that someone isn't a smoker as the reference category, and it's returned the vector of zeros and ones that indicate if someone is a smoker. So 0 if they're not, 1 if they are. Yeah, so Boolean true false values. So yeah, a 1 in that column means yes, they are a smoker, essentially. Similarly, for the region variable, the northeast region is the category level that has been used as the reference category, and what we have here are dummy codes showing a 1 if someone lives in the northwest, southwest, southeast, and southwest, having manually created our dummy coded categorical variables here. All right, so same here. If there's a region northwest 1, if there's a 1 there, they live in the northwest. If there's a 1 in this one, they live in the southeast, etc. So northeast has, again, as it was in the previous example, it's been used as our reference category. Despite the error here, what it says here, that's incorrect. My apologies. So having manually created our dummy coded variables for these two categorical IVs, we can now include them in the multiple regression model. Note also that creating these two dummy variables has removed the original smoker and region variable from the data frame. So if we go back up, look at the original data frame there, we had region and smoker, yeah, and they're no longer there now. They've been removed, as you can see, and these have been appended. Our dummy codes have been appended. So, okay, let's fit this new model, including region and smoker. So, what I'm going to do here is I'm going to explicitly include these dummy coded independent variables, so these new variables to the model. Okay, so similar to before, I'm going to call this model 2. We're going to use stats models formulas.ols. Our formula is going to be, again, we're going to pass it as a string using these r-star formulas. In double quotes, it's going to be expenses. RDV is a function of age plus BMI plus region northwest plus region southeast plus region southwest plus smoker, yes. Data is our data frame, this one above, and I'm using the dot fit all in one line. Let's look at the summary. Okay, so we get the same output as before, but what we can see in the above output is that adding the category of smoker to the model has significantly improved the model over the first model that we fitted where we didn't include smoker. Okay, so the model is obviously still significant. If we look at the F value here, we've got 6 and 1331 degrees of freedom. Our F statistic is 660.8. P is less than 0.001 in this case. My apologies, I've incorrectly put the degrees of freedom here for the between groups degrees of freedom, the model degrees of freedom. So we've still got a statistically significant model, but the R squared value indicating the amount of variance in insurance premium expenses that is explained has increased from, if you remember, the previous model accounted for about 12% of variance to about 75% in this case. So if you look at R squared for this second model, it's 0.749, so about 75% of variance explained by model 2. So it would appear that adding an independent variable indicating whether someone smokes accounts for a large amount of insurance expenses. So the coefficient for smoker yes is beta equals 23850. Okay, so it's kind of expressed it in scientific notation really. So it's 2.358 times e to the plus 0.4. So we'd have to move the decimal kind of 4 places to the right to get the actual slope. It's so steep. So it indicates that when someone smokes, their insurance expenses, the fact that it's a positive slope, are significantly higher than non-smokers. Okay, so smoker, no, that's the kind of the change essentially from. So I guess that's the change in expenses from not smoking to smoking, as opposed to being a slope, so to speak. Okay. So understandably that, this independent variable is a significant predictor in the model as well. So we can see, let me just make that table a bit easier to see. You can see there the t value associated with it, 57.68, p is less than 0.001. All right. Okay. Interestingly though, by adding the smoker categorical variable, the southeast category is also now a significant contributor to the model. So there's kind of something weird going on here interaction-wise. So what we're seeing for the southeast category is we've got a beta value of negative 1.39.16, and the t statistic associated with it is 2.163, and the p-value is 0.031. So The negative beta coefficient indicates that living in the southeast results in kind of a significantly lower insurance expenses premium compared to the northeast reference category. And the other region categories are still non-significant predictors of the DV expenses. But the two scale independent variables, age and BMI, are still significant and have positive beta coefficients associated with them. You can see those there, and they are both still significant. So age has a beta coefficient of 258.62 and a t-value of 21.68, p is less than 0.001, and BMI, body mass index, has a beta coefficient of 340.09, t-value of 11.86, p is less than 0.001. So positive values of both of these coefficients indicate that age and as your age increases, as your BMI increases, so do your insurance expenses. So I'm assuming this is all health insurance stuff. Okay, so let me summarize this. So what we've looked at here, we've kind of fitted a couple of multiple regression models. We've seen that by adding kind of an additional categorical variable, we've increased the amount of variance explained, and it's also changed whether a category of another independent variable is a significant predictor. So what this was about, this video, multiple regression models can be fitted using both scale and categorical variables to predict scores on a scale DV. When included categorical independent variables, it's important to check that they're correctly identified as an object category data type. If they are, then stats models will most likely automatically dummy code them in the analysis. If a categorical variable is not the correct data type and it's shown as an integer or something like that, it's necessary to create dummy coded versions of the variable. And you can do that using the pandas get dummy method. I've demonstrated how to do that. It's pretty straightforward. And when we dummy code something to include a categorical variable in a multiple regression model, it will take one level of the categorical variable as a reference level, and it will create n-1 new variables that indicate a difference of level to the reference category. Okay, so it will compare each other level to the reference category that has been chosen. All right, I hope that, so that was multiple regression, including a categorical predictor or including multiple categorical predictors, and using stats models. I hope it was useful, and thank you for watching and listening.